Imagine stepping out of a howling sub-zero blizzard. I mean, the wind is just biting at your face. You can barely see 10 feet in front of you, and the temperature is hovering somewhere around like -20 degrees.
Sounds absolutely miserable, honestly.
Oh, it is. But then you trudge over to this heavy wooden door that's set directly into the snowy ground. You heave it open, walk down a few earthen steps, and instantly the wind just stops.
Right.
You're suddenly standing in a lush, humid, 60-degree tropical oasis. You look around, taking off your heavy winter coat, and suddenly you realize there isn't a single electric heater anywhere in the room.
Just plants and dirt?
Yeah. Just dirt walls, a sloped translucent roof overhead, and rows of thriving green plants. So the question is this a scene from some science fiction movie set on a hostile ice planet? Or is it, the ultimate real-world hack to outsmart winter itself?
Well, I can tell you it is entirely real. What you're describing is a masterclass in manipulating the laws of thermodynamics. It's basically turning the Earth against the sky, if you will.
I love that phrasing.
Yeah, we're looking at a structural design that fundamentally rethinks our relationship with the elements. It takes everything we assume about heating and cooling and it flips it entirely upside down.
Well, welcome to this deep dive. Today we are staring at a massive stack of research on the table in front of us. I've got master gardener guides, overly ambitious homesteading manuals, deeply complex architectural blueprints, and some thermodynamic studies that honestly gave me a massive headache the first time I read them.
They're definitely dense. I mean, the math in those papers is intense.
Super intense. But our entire mission today is to decode the secrets of advanced greenhouse design for you. We are going to figure out exactly how you can manipulate the earth, the sun, and the very air itself to grow food in the harshest climates imaginable, and do it using little to no grid energy.
Which requires us to strip away a lot of our modern assumptions. Most of us are used to solving a cold room by just plugging something into a wall.
Right. We just crank the thermostat.
Exactly. We treat nature as this opponent to be battered back with fossil fuels and electricity. But the research we're looking at today treats nature, specifically the ground beneath our feet and the physics of moving air, as the engine itself.
So cool.
So we'll be starting with ancient earth-sheltered designs, moving through the really harsh realities of subterranean engineering, and then finishing with artificial intelligence climate control systems that literally use the physical geometry of air to create refrigeration out of nothing.
It's going to get wild. But I want to start by looking back before we look forward. Because going through these sources, I noticed that before anyone was using AI or, advanced polymers, they were just digging a hole.
What's the big hole in the ground? Yeah.
Yeah. I'm looking at this study from the Benson Agriculture and Food Institute at Brigham Young University from the 1990s. They were popularizing this concept called a Walipini.
The word Walipini is fascinating just on its own. It comes from the Aymara language, which is spoken by indigenous communities in the high-altitude Andes Mountains of Bolivia and Peru.
And the climate up there is just brutally unforgiving, right?
Oh, incredibly harsh. Extreme cold, intense winds. In Aymara, Walipini actually translates to place of warmth.
A place of warmth.
Right. It's an earth-sheltered cold frame. Most of us, when we hear the word greenhouse, we picture a beautiful glass or plastic tent sitting out in the middle of a yard.
Like a crystal palace sort of thing.
Exactly. But a Walipini destroys that visual completely. It is a rectangular pit dug 4 to 6 feet directly down into the earth.
I really had to adjust my mental model when I saw the diagrams and the research. Because a traditional glass greenhouse, while gorgeous, obviously is essentially a glass tent that leaks heat like an absolute sieve.
It's a thermodynamic nightmare.
It really is. You build this fragile bubble above ground, entirely exposed to the freezing wind. I mean, if it's 10 degrees outside, you have a millimeter-thin pane of glass acting as the sole defender for your delicate tomato plants.
And glass offers terrible insulation.
Right. So you end up having to blast a propane heater 24/7 just to fight the ambient air. It's just this endless war of attrition.
And you're constantly fighting those external elements, which is incredibly expensive and, frankly, environmentally disastrous.
Yeah.
The Walipini bypasses that war entirely by utilizing what we call earth sheltering.
Which means?
By digging a rectangular trench down 4 to 6 feet, you are enveloping the entire growing space in the Earth's natural thermal mass. You're hiding from the wind.
I was trying to come up with a visual for the listener who hasn't seen the blueprints. The best way I can describe it is taking a massive Yeti cooler, the kind you take camping, and burying it in your backyard so only the lid is flush with the grass.
That's a great image.
And then you just swap that opaque plastic lid for a sheet of clear glazing.
That analogy actually holds up beautifully, especially regarding the containment of energy. So you dig this pit, right? And the orientation is absolutely crucial. The longest side of the rectangle has to face the equator to capture the solar arc.
So if you're in the northern hemisphere, your pit faces directly south.
Exactly. You build the back dirt wall, the north wall a bit higher than the front dirt wall, and then you cap that angled opening with a sloped, translucent roof. Usually that's a double layer of agricultural plastic.
And that sloped roof seems to do a lot of the heavy lifting. The notes heavily emphasize the angle, like it seals the hole and traps the air, but more importantly, it creates this massive window for the winter sun.
Right, because the sun changes position.
Yeah, the winter sun hangs much lower in the sky than the summer sun. So this angled roof acts like a catcher's mitt for those low-hanging rays. It shoots all that solar energy straight down into the pit.
And that's where the magic happens.
So you're combining passive solar heating with the dirt walls, which are blocking all the wind. And the sources claim you can grow cool season crops like spinach, kale, Swiss chard, carrots in the dead of winter without ever plugging in a heater.
It sounds almost magical until you dig into the physics of why it actually works. I mean, calling it a cooler or a root cellar only really captures the shape. To understand how those plants survive a blizzard, we have to talk about what the dirt is actually doing.
Okay.
We need to look at the concept of the thermal constant.
Let's go there, because a lot of people, myself included before reading these thermodynamic papers, just think the ground is inert dirt. It's just mud. But these papers treat the ground like a massive engine.
Think about what the Earth actually is. It's a giant sphere heated from two opposing sides.
Okay.
Deep within, you have the molten core of magma radiating heat outward, and on the outside, you have the sun bombarding the crust with solar radiation every single day. But soil, rock, and clay are incredibly dense materials.
So they don't change temperature quickly.
Exactly. They conduct heat very, very slowly. Because of that density, the wild daily fluctuations of the weather on the surface, like a 90-degree afternoon followed by a 40-degree night, they just cannot penetrate deeply into the Earth.
It's like a buffer.
A huge buffer. By the time you get about 4 to 6 feet down, the soil temperature stops reacting to the daily weather entirely. It stabilizes into that thermal constant we mentioned.
I was reading the regional data charts on this, and it honestly blew my mind. If you go 4 feet down in a temperate climate, the dirt is just sitting there at a constant 50 to 60 degrees Fahrenheit all year long.
Yeah, completely stable.
So if it's 10 degrees outside with a 50-mile-per-hour freezing wind, the dirt walls inside your Walipini are just chilling at 55 degrees.
And that mathematical difference is the secret to the massive energy savings. Look at it this way. If your underground walls are radiating 55 degrees, and your plants need an ambient air temperature of, let's say, 70 degrees to really thrive, your solar gain only has to make up a 15-degree difference.
Oh, right, because you're starting from 55, not from 10.
Exactly. If you built a glass tent above ground in that same 10-degree blizzard, you would have to artificially generate 60 degrees of heat just to keep the plants alive.
But I want to stop and vocalize something here that I'm sure a lot of listeners are wondering, because I completely fell into this trap too. The ground isn't a magical furnace, is it?
No, definitely not.
Right, like it's not actively generating 55 degrees of heat from nothing.
No, it is not a furnace. It is a thermal buffer. And the structural data in our sources makes a very critical distinction here about transient conduction. The deep Earth does not automatically hold a greenhouse at 55 degrees everywhere on the planet.
Right?
The physics dictate that as you go deeper, the temperature stabilizes near the regional annual average temperature.
Oh, wow. Okay, so what does that look like if I try to build one of these, in different parts of the world?
Well, if you build a Walipini in Minneapolis, for instance, where the regional annual average temperature is much colder, say, somewhere around 46 degrees Fahrenheit, your deep soil temperature will stabilize at 46 degrees.
Okay, that makes sense.
If you build it in the high desert of the Andes, it stabilizes at whatever the annual average is for that specific region.
So if I build a Walipini in Minneapolis, and the walls are a constant 46 degrees, my plants are still going to freeze if I don't get some actual heat in there. The Earth is acting like a giant thermal bank account, but I still have to make deposits.
That is the perfect way to phrase it. You have to make deposits, and you make those deposits using the sun. This brings us to a really beautiful concept in the research called the flywheel effect.
The flywheel effect.
Yeah. Have you ever seen a mechanical flywheel on an old engine?
Yeah, like a massive heavy metal wheel that takes a ton of energy to get spinning. But once it is spinning, it keeps the engine running smoothly, even if the power dips, just because it has all that stored momentum.
Exactly. But instead of kinetic energy, we are storing thermal energy. The flywheel effect is driven by thermal mass. And thermal mass just refers to dense materials like earth, stone, concrete, or water that have a really high capacity to absorb heat energy during the day.
So they soak it up like a sponge.
They hold onto it and then they slowly bleed it back out as the surrounding air cools down at night.
So the mechanics of the pit look something like this. The sun rises, the radiation punches through that plastic roof, it hits the dense dirt walls and the floor. Those surfaces start absorbing the heat. They are charging up, like spinning up that heavy metal wheel.
Yep, getting faster and faster, thermally speaking.
Right. Then the sun goes down. The ambient air in the greenhouse starts to freeze because it's winter. But the walls, which have been baking all day, begin to slowly radiate their stored heat back into the air, keeping the space warm enough for the plants to survive the darkest, coldest part of the night.
The literature models this so elegantly. It describes the ground temperature as being driven by diurnal or daily and seasonal variations. The thermodynamicists model this as a harmonic function of time.
Okay, stop right there. Harmonic function of time sounds like a phrase specifically designed to fail college freshmen.
It really does.
Give me a visual. If I'm a listener trying to picture a harmonic function, what am I actually looking at?
Think of tossing a large rock into a perfectly still pond. You see waves rippling outward.
Right.
The wave has a peak, the crest, and a valley, the trough. On the surface of the Earth, the temperature is a massive wave. The peak is the blazing heat of July, and the trough is the freezing cold of January.
Okay. Yeah.
But heat conducts downward into the soil very, very slowly. As that temperature wave travels down into the dirt, the dirt gets thicker, so to speak. The amplitude of the wave, meaning the distance between the peak and the trough, it shrinks. It decays exponentially.
So the deeper you go, the smaller the wave gets until the line is completely flat. That's the thermal constant.
Yes. And here's where the time part of the harmonic function comes in. Because the heat moves so slowly through the dense soil, there is a depth-dependent phase shift. This creates what we call thermal lag.
Thermal lag.
Right. The intense baking summer heat that's absorbed by the surface soil in July conducts downward so agonizingly slowly that it doesn't actually reach the deep subsoil of the Walipini walls until December.
Are you kidding me? Wait, so the heat keeping your plants alive in a December blizzard is actually the stored ghost of the summer sun arriving 6 months late?
Precisely. It's a beautiful system. And conversely, the deep freezing cold of January slowly penetrates the earth and finally arrives at the subsoil walls in July. So it acts as natural air conditioning during the summer heat wave.
That is just incredible. Nature's perfect delayed climate control.
Exactly.
And the sources point out that you don't just have to rely on the dirt walls either. You can actually optimize this flywheel effect. The master gardener guides are obsessed with this concept of absorptance.
Oh, absorptance is huge. It's just a measure of how much solar radiation a specific color or material drinks in versus how much it reflects away. White surfaces, for example, have an absorptance of maybe 0.25 to 0.4. They are highly reflective.
Right, which is why you wear a white t-shirt in the summer.
Exactly. You do not want white walls in a passive solar greenhouse if you are trying to capture heat. Black or dark surfaces have an absorbance of 0.8 to 0.9. They swallow almost all the solar radiation that touches them.
Which perfectly explains a really weird detail I found in the homesteading photos. You look at these passive solar setups built in places like the Trans-Himalayas, and the back north walls are either painted flat black, or there's just a massive wall of black 55-gallon drums filled with water.
Yep, stacked right against the back wall.
I was wondering about that. Why use water instead of just piling up more dirt or rocks?
Because water is the undisputed king of cheap thermal mass. It has an incredibly high specific heat capacity. Just to give you the numbers, a single 55-gallon drum of water can store approximately 4,500 British thermal units, or BTUs, of heat energy for every 10-degree Fahrenheit change in temperature.
Okay, let's put that into perspective. A BTU is roughly the heat of one lit match. So that single barrel is absorbing the heat of 4,500 matches just by warming up 10 degrees in the sun.
Exactly. And by painting those drums flat black and stacking them right where the low winter sun strikes the back wall of the Walipini, you're creating a massive, hyper-efficient thermal battery.
It's so smart.
The black paint absorbs the radiation, the water rapidly soaks up the heat, and then it gently warms the greenhouse all night. And as an added bonus, many growers actually use that pre-warmed water for their irrigation lines the next morning.
Oh, so they aren't spraying freezing cold water onto the plants.
Right, which prevents them from shocking the plant's root systems with freezing hose water.
It's just layer upon layer of efficiency. I mean, the physics are so elegant. You dig a hole, use the Earth's thermal lag, you paint some water barrels black, and you capture the winter sun. It sounds completely foolproof.
It does sound that way.
And honestly, because it sounds so brilliantly simple, you get onto YouTube or, homesteading blogs, and you see 1,000 guides promising you can build a subterranean oasis for under $1,000.
Ah, yes. The allure of the budget build. It is
Yeah.
very powerful.
I mean, who wouldn't want that?
Yeah. Right. And the initial material list looks incredibly cheap. They suggest using salvaged double-pane windows from a Habitat for Humanity restore for $10 a pop. They suggest using reclaimed lumber, free-fill dirt, and just shoveling local gravel for the floor.
You're essentially trying to replace the high cost of modern manufactured insulation with the sweat equity of a shovel.
But the research papers paint a very different, much darker picture of what happens when that DIY ambition meets high-altitude freezing reality. I'm looking at this empirical failure rate, and it is honestly staggering.
Yeah, I saw that. What was the number?
The data reveals that 68% of these budget subterranean greenhouse builds fail completely.
68%. That's huge.
It's massive, and they do not fail because the thermodynamic theory of a Walipini is flawed. They fail because people drastically underestimate the brutal engineering realities of building an unlined pit in the earth.
What's the main thing that goes wrong?
The absolute primary culprit that destroys these projects is water infiltration.
I can easily imagine why. I mean, if you dig a giant 6-foot-deep rectangular hole in your backyard, you haven't just built a greenhouse. You've built a basement with no house on top to protect it.
You've built a swimming pool, basically.
Exactly. If you don't manage the groundwater, the very first time you get a heavy rainstorm or the spring snowmelt happens, your beautiful 55-degree oasis turns into a freezing mud pit.
The type of soil you are excavating is the first variable that budget builders always seem to ignore. The sources detail how soil mechanics basically govern the entire project. If you are digging in clay-heavy soil, which is very common in regions like the upper Midwest of the United States, you will be thrilled at first.
Because it holds its shape.
Right. The dirt walls will hold their shape beautifully like pottery. You barely need any lumber to shore them up. But clay has a fatal flaw. It retains water, and when it gets wet, it swells.
And when it swells, it pushes.
It creates immense hydrostatic pressure. As the ground outside the greenhouse becomes saturated, millions of pounds of waterlogged clay push inward against your excavated walls.
What does that actually look like in practice? Are we talking about a slow crumble or something more dramatic?
If you do not have robust retaining walls and drainage, it looks like a catastrophic structural failure. The walls will bulge and eventually cave in, or at best, water will constantly weep through the clay and flood the floor of your greenhouse, literally drowning the roots of your plants in freezing mud.
Wow.
Now, if you have the opposite problem, if you build in sandy or loamy soil, the water drains away beautifully. You have almost zero hydrostatic pressure. But sand has no structural integrity.
Right, it's like digging a hole at the beach. As soon as you dig down 2 feet, the sides just start cascading inward.
Right.
You'd have to spend an absolute fortune on heavy timber retaining walls just to keep the earth from swallowing your greenhouse before you even put the roof on.
So you really have to know your dirt. But the insidious water creeping up from below is only half the battle. The water falling from above, specifically in the form of snow, is what destroys the roof.
Let's talk about the roof failures, because this is where the DIY aesthetic becomes genuinely dangerous. The blogs tell you to just slap some reclaimed windows or stretch some 6mm plastic over a basic wooden frame made of 2x4s.
In a high-altitude or cold climate, an unbraced single-layer roof is a disaster waiting to happen. People forget that wet snow is incredibly heavy. The structural data indicates that these simple budget frames frequently collapse under a snow load of just 15 to 20 pounds per square foot.
I want to translate 20 pounds per square foot into a visual for you listening. If you have decent-sized greenhouse roof, say 10 feet by 20 feet, that's 200 square feet. If you get a wet, heavy blizzard that drops 20 pounds of pressure per square foot, you suddenly have 4,000 pounds of weight sitting on your flimsy, reclaimed 2x4s.
It's massive.
That is the equivalent of parking a mid-sized sedan on top of some plastic sheeting. Of course it collapses. You wake up after a blizzard and you find a shattered mess of glass, splintered wood, and crushed crops. So how do the architectural guides solve this?
It requires serious structural engineering. First, the roof must be pitched correctly. The optimal angle for the glazing is calculated mathematically. It is your geographic latitude plus 15 to 20 degrees.
Okay, why that specific formula? Why not just make it a standard A-frame?
2 reasons. First, that steep angle presents the largest possible surface area perfectly perpendicular to the low winter sun, which maximizes your solar gain.
Okay, that makes sense for the heat.
Second, that angle creates a steep enough slope that heavy snow simply cannot accumulate. The snow will naturally shear off the slick plastic or glass before it can ever reach that critical 20-pound threshold.
So it just slides right off.
Exactly. But even with a steep roof, you cannot rely on 2x4s. You must engineer cross-braced trusses.
A truss. For the listener, a truss is that triangular wooden web you see when you look up into the rafters of an unfinished garage.
Exactly. The triangle is inherently structurally rigid. A cross-braced truss takes the downward vector weight of whatever snow does stick and distributes that force out to the edges and down into the structural footings, rather than letting the weight press directly down on the fragile middle of the roof span. You really have to build trusses rated for at least 30 pounds per square foot if you want to survive a serious winter.
Okay, so we've fixed the roof with physics and geometry, and we understand the danger of the dirt walls caving in. But I want to push back on another huge myth I saw circulating in these sources.
Let's hear it.
It's the primary reason the internal temperature fails, even if the walls don't collapse. It's the insulation myth. People think, I am surrounded by 4 feet of thick earth. Earth is dense. Therefore, I have the ultimate insulation. It's basically a bunker. I must have an R20 rating.
That is such a dangerous, fundamental misunderstanding of thermodynamics. We need to distinguish between thermal mass and thermal insulation. They are absolutely not the same thing.
How so?
Well, the R value of a material measures its resistance to conductive heat flow. A high R value means heat struggles to pass through it. Modern fiberglass insulation that you put inside the walls of a residential house might be rated at R13 or R20.
Because it's full of fluffy air pockets that trap the heat, right?
Correct. But the engineering data clearly shows that undisturbed, wet soil has a shockingly low R value. It is only about 0.67 per inch of thickness.
I did the math on this while I was reading. If you dig down 4 feet, that is 48 inches of dirt. 48 multiplied by 0.67 gives you a total insulation value of roughly R3.2.
An R value of 3.2 is practically negligible in a sub-zero climate.
It's nothing. It's the equivalent of trying to survive a blizzard wearing a wet cotton t-shirt. It provides almost no resistance.
This is why the distinction is so vital. The Earth has incredible thermal mass. It can soak up and hold a massive amount of heat. But it is a terrible insulator. Heat travels horizontally through it with ease.
Oh, I see where this is going.
If you build a Walipinis and do not insulate the perimeter, the precious solar heat you capture inside your greenhouse during the day will just bleed outward horizontally into the infinitely cold, freezing topsoil surrounding your pit. The Earth will literally suck the heat out of your greenhouse.
So the very thing providing your thermal mass is acting like a heat sink.
Yeah.
How do the engineers solve this? How do we stop the budget builds from failing?
Yeah.
It sounds like you really have to spend the money on the invisible infrastructure.
You absolutely do. To combat the water infiltration and the hydrostatic pressure we talked about earlier, you must install a continuous 6 mil polywater barrier behind the unlined earthen walls. You also have to dig a trench around the perimeter of the floor, fill it with crushed gravel, and lay down perforated French drains.
How does a French drain actually stop hydrostatic pressure, though?
Well, a French drain is simply a pipe with holes in it, buried in a trench of loose gravel. Water always takes the path of least resistance. So instead of pushing millions of pounds of pressure against your earthen wall, the groundwater hits the loose gravel, drops into the perforated pipe, and is safely diverted by gravity to a daylight outlet down the hill, completely away from your structure.
Okay, so the water is diverted. What about the R value problem? How do we stop the heat from bleeding horizontally into the frozen topsoil?
You have to sever the thermal bridge. Engineers highly recommend installing EPS, expanded polystyrene rigid foam board insulation below grade.
Just big foam boards.
Yes, but EPS is a closed cell foam. Because the cells are closed, water cannot penetrate it, so it maintains its high R value even when it's buried in wet dirt. You bury these EPS boards vertically around the outer perimeter of the greenhouse walls, going down a few feet.
So you are basically drawing a hard thermodynamic boundary line. You are telling the heat you can warm up the dirt inside this perimeter, but the EPS foam is going to stop you from bleeding out into the rest of the yard.
Exactly. By combining the French drains, the EPS insulation, and the cross-braced trusses, you transform a risky, flooded mud pit into a highly engineered, reliable structure. But you really have to respect the physical forces at play.
Which makes a lot of sense. I mean, passive thermal mass is wonderful, but relying entirely on the low R value of dirt and the passive radiation of black water barrels has its limits.
Very strict limits.
Especially in extreme high-altitude climates. Because what happens if the sun doesn't shine for a week during a massive blizzard? The flywheel stops spinning. Your thermal bank account goes bankrupt. If the passive systems have limits, how do we turbocharge this subterranean setup? We need to turn our passive pit into an active engine.
And this is where we leave ancient agricultural practices behind and enter the realm of modern, highly effective geothermal engineering. We are talking about active geothermal integration, or what the literature refers to as a climate battery.
A climate battery. I love the sound of that.
Alternatively, the technical term is an earth-air heat exchanger, or EAE.
Walk me through the actual physical construction of this. Because we aren't just letting the dirt walls absorb whatever sunshine happens to hit them anymore. We are heavily modifying the floor of the greenhouse before we even plant anything, right?
Yes. Before you lay down your gravel floor and build your planting beds, you bring in the excavators and dig much deeper, usually 4 to 8 feet straight down below the floor of the Walipini.
Okay, so we're going really deep now.
In that deep trench, you lay down a massive serpentine network of perforated, corrugated plastic pipes. Usually, this is high-density polyethylene or HDPE tubing. You zigzag these pipes back and forth across the entire footprint of the floor. You connect all these buried tubes to large vertical manifold pipes at either end, attach an automated inline fan system, and then you bury the entire network back up with soil and gravel.
Okay, so I'm standing in a greenhouse, and there is a massive network of plastic tubes buried 4 feet beneath my boots. What is the fan doing?
Well, imagine it is a sunny winter afternoon. It might be 20 degrees outside, but inside your sealed Walipini, the sun is just pounding through the plastic roof. The air at the very peak of the greenhouse, the apex of the roof, gets incredibly hot and very humid from the transpiring plants.
Yeah, heat rises.
Exactly. In a traditional passive system, you would have a major problem right now. You would have to open a vent to let that heat escape. Otherwise, you would literally bake your plants.
Right, but if you do that, you just throw all that precious heat away into the freezing sky.
But with a climate battery, you don't vent it. The thermostat detects the heat at the peak, and the fans kick on. They forcefully draw that hot, humid 80-degree air from the ceiling and push it violently down the manifold and into the subterranean network of pipes.
I have to stop you there. We are taking hot air and blowing it into cold dirt. If you're listening to this right now, you're probably as skeptical as I was when I first read this.
It sounds counterintuitive.
It sounds like a terrible way to store heat. Air doesn't hold heat very well. If you blow hot air through a cold pipe, it just cools off instantly.
You are correct that air has a low specific heat capacity. That is called sensible heat transfer. The hot air simply warming up the cooler pipe walls. But sensible heat transfer is not the secret of the climate battery. The secret relies entirely on the humidity. It relies on the physics of latent heat.
Okay, walk me through the chemistry of latent heat. I need to understand this.
When you push hot, humid air into those cold subterranean pipes, the air hits the cold plastic and rapidly drops in temperature. Cold air simply cannot hold as much moisture as hot air. So the water vapor suspended in that humid air undergoes a phase change. It condenses into liquid water droplets on the inside of the buried bite.
Condensation, like water droplets forming on the outside of a cold can of soda on a hot summer day.
Exactly like that. But here is the thermodynamic magic. Creating water vapor requires energy. When water boils on your stove and turns into steam, it is absorbing heat. Therefore, when water vapor condenses back into a liquid, it must release that exact same amount of energy.
Wait, really?
Yes, this is called the latent heat of vaporization. When that vapor condenses inside the buried pipes, the molecular bonds change, and it releases a massive sudden spike of thermal energy directly through the pipes and into the surrounding subterranean soil mass.
Wait, seriously, you are literally using microscopic water droplets condensing on plastic to inject massive amounts of heat into the dirt.
It is breathtakingly efficient. The phase change of water releases far more energy into the soil than you could ever achieve by just blowing dry, hot air around. You are dramatically increasing the thermal storage capacity of the ground.
I am completely mind blown by that. So we are treating the Earth beneath the greenhouse exactly like a giant rechargeable battery. But instead of plugging it into an electrical outlet to charge it with electrons, we are plugging it into hot, humid air and charging it with the latent heat of water vapor.
It is a brilliant way to conceptualize it. During the day, you charge the battery, the hot air goes down, the condensation deposits the heat into the soil mass, and the air that finally exhausts out the other end of the pipes and back into the greenhouse floor is now cool and dehumidified,
Oh, wow.
which actually prevents your plants from overheating in the afternoon sun.
So you are capturing the heat, storing it, and getting free air conditioning at the very same time. And what happens when the sun goes down and the blizzard rolls in?
At night, when the temperature in the greenhouse plummets, the system automatically reverses. The fans pull the freezing cold air from the floor of the greenhouse and push it down through the pipes. But remember, those pipes and the surrounding cubic tons of soil are now fully charged. They are radiating the heat deposited during the day.
So the cold air warms up.
Yes, the cold air sweeps through the pipes, absorbs that stored heat, and warm air is discharged back into the growing space, maintaining a perfectly stable, safe temperature for the crops all night long.
That is just phenomenal engineering. But what stops the system from running constantly? I mean, if the fans just run 24/7, wouldn't you just suck all the heat out of the dirt battery too fast and drain it completely?
That is where the concept of energy balance governs the entire system. Advanced setups are strictly controlled by algorithmic thermostats. Heat transfer only occurs when there is a temperature differential.
What does that mean in practical terms?
When the air temperature inside the greenhouse structure drops to equal the temperature of the subsoil battery, they are in equilibrium. Heat stops moving. When the sensors detect this equilibrium, they shut the fans off. You only spend the electrical energy to run the fans when there's actually useful heat to harvest or deploy.
Which means your operating costs fall off a cliff. You don't need a massive, expensive propane heater running all night. You just need a tiny amount of electricity to run an inline fan, which you could easily power with a single solar panel and a deep cycle battery.
The reduction in greenhouse gas emissions, the removal of fossil fuel dependency, and the drop in sheer operational cost is profound. You are harvesting excess solar energy that would otherwise be vented out and completely wasted, storing it chemically in the earth via latent heat, and retrieving it precisely when the plants need it. It makes growing delicate crops like tomatoes or citrus in a frozen tundra not just scientifically possible, but economically viable.
Okay, so let's take a breath, because we have officially conquered winter. We've tapped into the deeper thermal constant. We've engineered away the hydrostatic pressure and the roof-crushing snow loads. We've built a giant rechargeable dirt battery powered by water vapor. But I was looking at the end of this research stack, and here's where the narrative takes a really sharp turn.
It does.
Because solving the winter freezing problem creates a totally new, highly lethal problem for the summer.
Yes, the problem of dangerous overefficiency.
Right. We have spent all this time designing a sealed, highly insulated, earth-sheltered structure optimized to aggressively trap solar energy and aggressively store heat. What happens when spring rolls around? Or during the peak of July? Or what if you were trying to build this advanced greenhouse in Florida or the Middle East where it's already hot?
It becomes a huge issue.
Suddenly, trapping all this heat and sealing the structure up tight turns the greenhouse into a literal death trap. Extreme heat and stifling humidity. How do commercial agricultural setups handle this without just slapping a massive power-hungry industrial air conditioner on the roof?
Which brings us to the final frontier of our deep dive, the modern marvels of advanced climate control. We have to look at how alternative technologies, specifically desiccants and evaporative cooling, can actually save the plants. But to understand why these massive commercial setups use such bizarre technology, we first have to understand what a plant actually wants. We have to talk about VPD.
VPD, vapor pressure deficit. I saw this acronym plastered all over the commercial agriculture blueprints. Let's break this down, because it sounds intimidating, but the master gardeners treat it like the absolute holy grail of plant health.
Vapor pressure deficit is the mathematical difference between the amount of moisture currently in the air and how much moisture the air could theoretically hold when it is completely saturated. In simpler terms, it is a measure of the drying power of the air. It dictates how easily a plant can breathe.
Plants breathe water, essentially, they sweat.
The technical term is transpiration. Plants release water vapor through microscopic pores on the underside of their leaves called stomata.
So if I'm a plant, how does VPD affect my ability to transpire? I want to use a sensory analogy here. Imagine you are a human being trying to go for a jog in a sauna while wearing a plastic raincoat.
That is a highly uncomfortable but very accurate analogy for low VPD. If the air in the greenhouse is incredibly hot and heavily humid, meaning the VPD is very low, the air is already saturated, it is full of water. The plant tries to open its stomata to transpire, but the water vapor has nowhere to go.
Because the air can't hold any more water.
Exactly. The plant's sweat won't evaporate. Because it cannot transpire, it cannot pull cool water and vital nutrients up from its roots. The plant essentially suffocates, overheats, and becomes highly susceptible to fungal diseases like powdery mildew.
And what about the opposite, high VPD? What if the air is incredibly dry, like a desert?
If the VPD is too high, the drying power of the air is immense. The plant opens its stomata, and the dry air violently rips the moisture out of the leaves. The plant transpires way too fast, losing water quicker than its root system can pump it out of the soil. The cells lose turgor pressure, the plant wilts rapidly, and it dies of dehydration.
So it's a tightrope walk. The literature shows that plants require a very specific, narrow VPD range, typically between 0.8 and 0.9 kilopascals, to avoid heat stress, disease, and yield loss. In a sealed, hot Walipini in the summer, the humidity from the wet soil and the transpiring plants builds up almost instantly. The VPD drops dangerously low into the sauna zone. You absolutely must cool the air and remove the humidity.
And this presents a massive engineering hurdle. The traditional way we manage temperature and humidity in an office building or a residential home is with vapor compression air conditioning, what the architectural sources call VAC.
VAC is just the standard AC unit sitting outside everyone's house, making that loud humming noise.
Yeah,
Sorry.
exactly. VAC uses a very complex, energy-intensive cycle. A compressor physically squeezes a chemical refrigerant gas, it condenses into a liquid, expands through a valve, and evaporates in a coil, absorbing heat. While VAC provides highly consistent cooling and excellent dehumidification, it has two fatal flaws for sustainable off-grid agriculture. First, the compressor requires an enormous amount of continuous electrical power.
Which defeats the whole purpose of building an off-grid greenhouse. If you have to plug into a massive power plant to run your AC, you might as well just build a warehouse.
Precisely. And second, many of the chemical refrigerants used in these systems are potent greenhouse gases. Leaks are inevitable over time. So we need a way to drop the temperature and control the humidity without using a massive AC compressor. This leads us to evaporative cooling.
Now, evaporative cooling is something a lot of people in dry climates like Arizona or Nevada might be familiar with. They call them swamp coolers.
Swamp coolers are the most common form of direct evaporative cooling, or DEC. The mechanism is very simple. You take a fan and you force hot, ambient outdoor air through a thick pad that is soaked in water. The sensible heat in the air causes the liquid water in the pad to evaporate into a vapor. This phase change absorbs heat energy out of the air, so the air blowing out the other side of the wet pad is significantly cooler.
Sounds great. Problem solved. We just slap a swamp cooler on the Walipini.
I must stop you there. Think back to VPD. What is the side effect of a swamp cooler? Direct evaporative cooling drops the temperature, yes, but it dramatically raises the humidity of the air because you are literally blowing evaporated water vapor directly into the airstream.
Ah, right. The sauna analogy.
Yeah.
If the greenhouse is already struggling with high humidity from the transpiring plants, turning on a swamp cooler just blows more wet air into the room. The plants will choke.
Exactly.
So we are stuck. We need a way to cool the air using the cheap magic of evaporation, but without adding any moisture to the air the plants breathe. That sounds physically impossible.
It sounds impossible, but it is not. It was solved by a marvel of thermodynamic engineering called the Masat-Senko cycle, heavily referenced in the commercial climate control sources as an MEC system.
The Masat-Senko cycle. I read this section 3 times. Walk me through how this wizardry works, because it is honestly blowing my mind.
The MEC is a highly advanced type of indirect evaporative cooling. It utilizes a specially designed heat exchanger made of ultra-thin, highly conductive plates. These plates create alternating channels. One channel is completely dry. The channel right next to it, separated by the thin plate, is wet.
Okay, I have a dry tunnel and a wet tunnel side by side.
Let's trace the path of the air. The hot ambient air from outside is blown into the dry channel. As it flows down this dry tunnel, the walls of the tunnel cool it down sensibly, meaning the temperature of the air drops. But because it is in a dry, sealed tunnel, its moisture content does not change at all.
It's getting colder, but it's not getting wetter.
Exactly. But here's the absolute genius of the Mesot-Senko cycle geometry. Once that air reaches the end of the dry channel, it is now significantly cooled. The system takes a small portion of this newly cooled dry air and redirects it in a U-turn, sending it back the opposite direction through the adjacent wet channel. This redirected air is called working air.
So we take cold, dry air and push it over a wet surface.
Yes, and as this already cool, highly dry working air flows over the wet surface, water evaporates into it very rapidly. Evaporation absorbs heat. So this evaporating water absorbs massive amounts of thermal energy from the thin plate that separates it from the dry channel.
Wait, I think I'm getting it. The air evaporating in the wet channel is actually acting as a refrigerant to freeze the walls of the dry channel next to it.
Yes. Because the working air entering the wet channel was already pre-cooled by its trip down the dry channel, it has an artificially massive capacity to cool through evaporation. It is a cascading, compounding effect. The wet channel gets colder, which makes the dry channel colder, which makes the working air entering the wet channel even colder.
That is just brilliant. It's a feedback loop of cold.
This cascading geometry allows the MEC system to cool the air in the dry channel all the way down to the dew point, the absolute lowest theoretical temperature possible for that air mass, without adding a single drop of moisture to the main airstream that eventually enters the greenhouse.
You are creating air conditioning level refrigeration, but you are keeping the air completely dry. You get all the temperature dropping power of a quam cooler, but absolutely none of the humidity penalty. It is the perfect cooling mechanism.
And the true beauty is the energy efficiency. Because there is no mechanical compressor squeezing chemical refrigerants, the only electricity the MEC requires is a small fan to push the air through the channels and a tiny water pump to keep the wet channels damp. It uses a fraction of the electricity of traditional air conditioner.
Okay, so the Mesot-Senko cycle handles the brutal summer heat without adding humidity. But we still have one final boss to defeat. What if the outside air you were pulling into the system is already incredibly humid?
That's a great question.
Yeah, like what if you were building this advanced greenhouse in the sweltering humidity of Florida or the deep jungle? Or what if the transpiration of thousands of plants inside the sealed Walipini is just producing too much moisture? How do we physically rain the water out of the air to maintain that perfect VPD?
When evaporative cooling alone cannot manage the vapor pressure deficit, the advanced setups turn to desiccant dehumidification systems. Desiccants are hygroscopic materials. This means they possess a natural chemical affinity to absorb moisture directly out of the surrounding air. They pull it in at a molecular level.
Desiccants, and let me try to bring this down to earth for a second. We've all seen desiccants. Those are those little white packets that say "do not eat" that you find inside a new pair of shoes or at the bottom of a bag of beef jerky, right? The silica gel.
That is exactly what they are. Silica gel is a very common solid desiccant used to keep consumer goods dry. But in advanced commercial greenhouse climate control, we scale that exact chemical concept up to a massive industrial size. They act like giant engineered chemical sponges to violently wring the water vapor out of the greenhouse air, ensuring the plants can actually breathe.
How does a beef jerky packet scale up to an industrial greenhouse? What does the machine look like?
The sources outline two main architectures, solid desiccants and liquid desiccants. In a solid system, the most common setup is a large, slowly rotating desiccant wheel. The wheel looks like a giant slice of honeycomb, constructed of corrugated material that is deeply coated in advanced desiccants.
What kind of materials? Just tons of silica gel.
Silica gel is used, as well as zeolites, but the bleeding edge of the technology utilizes metal organic frameworks, known in the literature as MOFs. These MOFs, such as CuBTC or aluminum fumarate, are engineered in laboratories at the molecular level to possess unimaginably massive surface areas. A single gram of an MOF can have the internal surface area of a football field. They are custom designed to trap water vapor molecules like a microscopic net.
So you hook up a massive fan and you blow the sweltering humid greenhouse air through this slowly spinning honeycomb MOF wheel. The chemical sponge just grabs the water molecules right out of the airstream, and the air comes out the other side incredibly dry.
Correct. The dehumidification is nearly instantaneous. However, there is a catch. Eventually, the chemical sponge gets completely full. The desiccant becomes saturated with water molecules and cannot absorb any more moisture from the air.
Well, you can't just throw away a multi-thousand-dollar industrial MOF wheel every 3 days like you throw away a beef jerky packet. What do you do?
You have to perform what engineers call regeneration. You have to dry the sponge out so it can be used again. As the wheel slowly rotates, the saturated portion of the honeycomb moves out of the main greenhouse airstream and enters a secondary isolated chamber. In this chamber, a stream of extremely hot air is blown through the wet honeycomb.
Why hot air?
The intense heat physically breaks the weak chemical bonds holding the water molecules to the desiccant material. It vaporizes the trapped moisture, forcing it out of the wheel, and this wet exhaust air is vented completely outside the greenhouse. As the wheel continues to turn, this newly dried, regenerated section rotates back into the main airstream, hungry to absorb moisture once again. It is a continuous, never-ending cycle.
But wait, I have to stop you. If we have to generate a stream of extremely hot air to dry the wheel, don't we have to use a massive electric heater? Aren't we right back to wasting a ton of grid energy, ruining our sustainable off-grid goal?
That is the genius of the engineering. Desiccant regeneration does not require high-grade electrical energy. It only requires low-grade thermal energy. The required heat can be captured from the waste heat of other mechanical equipment, or, as is most common in these advanced eco-greenhouses, it is generated using solar thermal collectors mounted on the roof.
Solar thermal collectors, like tubes of water painted black that get boiling hot in the sun.
Exactly. You are literally using the free power of the sun to boil the water out of your chemical sponge. It requires almost zero electrical grid input.
You mentioned liquid desiccants as well. Do they work the same way?
The chemical principle is identical, but the delivery mechanism changes. Instead of a spinning solid wheel, liquid systems use a highly concentrated saline solution, often harsh salts like lithium chloride, calcium chloride, or magnesium chloride mixed with water.
Just a super salty liquid.
Yes, the humid greenhouse air is blown upward through a packed tower, while this liquid desiccant is continuously sprayed downward like a shower. As the air passes through the salty rain, the liquid rapidly absorbs the moisture from the air. The air leaves the tower completely dry.
And I'm guessing the salty rain gets watered down over time because it's absorbing all that humidity.
Exactly. The solution becomes diluted. So the diluted liquid is continuously pumped to a separate regenerator unit. Here again, solar heat is used to literally boil off the excess water, reconcentrating the salty desiccant so it can be pumped back to the shower tower and used again. Liquid systems are particularly prized by engineers because they can be pumped into storage tanks, acting simultaneously as a powerful dehumidifier and an incredibly dense liquid thermal mass.
Okay, I want to pull all of this together for the listener. Let's design the ultimate endgame hybrid system based on all these disparate blueprints in front of us. Imagine you have built your deep, earth-sheltered Walipini. You have your cross-braced roof and your French drains. It is high noon in the absolute dead of summer in Florida. It is 95 degrees, and the air is swampy and thick with humidity. The plants are suffocating. What happens?
The system activates. The sweltering ambient outdoor air is drawn into the intake. The very first thing it hits is the solar regenerated desiccant wheel. The MOFs in the wheel aggressively strip away the massive humidity. The air emerges from the wheel incredibly dry. However, the chemical process of absorption actually releases a small amount of latent heat.
Okay, so the air is now desert dry, but it's even hotter than when it entered.
Correct. Next, that hot, dry air is forced through a standard sensible heat exchanger which pulls the worst of the heat out. Finally, this pre-cooled bone-dry air enters the Mesotsemco cycle evaporative cooler. Yes. Because the air was perfectly dried by the desiccant wheel, the MEC can evaporate water inside its working channel with devastating efficiency. The cascading evaporative effect chills the air in the dry channel all the way down to the dew point.
So the air that finally bursts out of the ductwork and sweeps across the leaves of your delicate tomato plants is perfectly cool, refrigerator crisp, and precisely dehumidified to maintain that exact 0.8 to 0.9 kilopascal vapor pressure deficit. The plants can transpire perfectly.
It is absolute climatic perfection. You are providing pinpoint surgical precision for temperature and humidity. And because you're using passive solar energy to regenerate the desiccant sponge and the natural physics of evaporation to chill the air via the MEC, you are achieving this using only a tiny trickle of electrical power for a few fans and pumps. You drastically increase your plant yields, you completely eliminate fungal diseases by controlling the moisture, and you operate almost entirely off the grid.
And as I read the final notes here, I realize that this isn't just a farmer running around turning dials and checking thermometers. The most modern sources emphasize the integration of artificial intelligence.
Human reaction time is simply too slow to manage the cascading thermodynamic variables of a system this complex. Artificial intelligence is the final, necessary layer. Modern smart greenhouses run these entire hybrid systems autonomously.
What is the AI actually doing, though?
The AI algorithms are constantly analyzing massive, real-time data streams from dozens of microsensors distributed throughout the structure. It is monitoring the deep subsoil temperature, the moisture of the EPS-insulated perimeter, the ambient air humidity, the internal temperature gradients, the exact angle of the solar radiation, and even advanced optical sensors that measure the microscopic transpiration rates of the plant leaves themselves,
It's monitoring the sweat of individual plants.
and reacting to it in milliseconds. The AI proactively adjusts the rotation speed of the desiccant wheel to catch a spike in humidity. It modulates the microvalves of the MEC water pump to drop the temperature by a fraction of a degree. It decides exactly when to reverse the fans on the underground climate battery to tap into the latent heat stored in the dirt. It orchestrates all of these physical components to perfectly match the specific biological needs of the plants at any given second.
It's a symphony. It's a literal symphony of dirt physics, complex chemistry, structural geometry, and computer science.
It represents the absolute pinnacle of controlled environment agriculture. We have taken the raw, brutal chaos of the natural climate and subjected it to perfect, elegant order.
So what does this all mean? Let's zoom out and synthesize this incredible journey we've just been on. We started with a simple hole dug in the high Andes, the ancient Walipinis. Just a pit in the dirt, relying on the deep, stable thermal constant of the Earth's crust to provide a buffer against the freezing wind.
From that hole, we layered on the complex thermodynamic physics of thermal mass and the flywheel effect. We learned how dense materials like earth, stone, and black barrels of water act as thermal batteries, soaking up the winter sun and delaying its release across massive shifts in time to keep plants alive in the dark.
We confronted the harsh, unforgiving realities of subterranean engineering. We learned that DIY hubris and a shovel will only get you a collapsed mud pit. We learned that you must respect hydrostatic pressure with French drains, severe snow loads with cross-braced trusses, and the surprisingly terrible R-value of dirt by utilizing closed-cell EPS foam insulation.
Then we evolved the passive pit into an active thermodynamic engine using a climate battery. We forced hot, humid air deep underground to harness the incredible unseen power of the latent heat of vaporization, turning water droplets into a massive heat injection system.
And finally, we confronted the lethal problem of the summer heat. We didn't surrender to power-hungry AC compressors. We used AI-driven wizardry. We deployed solar-regenerated chemical sponges to wring the moisture from the air, and we used the Mesotsenko cycle to create refrigeration out of nothing but thin plates, dry air, and the magic of evaporation.
It is a comprehensive, scalable blueprint for outsmarting the elements. By deeply understanding the physics of heat transfer and moisture mechanics, we have engineered a way to cultivate fragile life in extreme environments that actively want to extinguish it.
Which brings me to a final thought I had while compiling these sources. It's a provocative idea, and I want you to really mull this over. Throughout this entire hour, we've been talking strictly about agriculture. We've been talking about saving spinach and tomatoes and citrus fruits. But if we can engineer a subterranean structure to maintain perfect, humid, 65-degree tropical weather, while a sub-zero blizzard rages outside and we can do it using almost zero grid energy, why are we only using this technology for plants?
It is the most profound question raised by this entire field of study. If we can seamlessly integrate earth-sheltering, active, latent heat climate batteries and AI-driven desiccant cooling to perfectly manage vapor pressure deficit and human comfort, what does this mean for the future of human habitation itself?
Think about the housing crisis. Think about sustainable housing in the most extreme, inhospitable environments right here on Earth. Imagine communities in the freezing darkness of the Arctic Circle or in the scorching, lethal deserts of the Middle East, living in incredibly comfortable, naturally regulated, earth-sheltered ecologies that don't rely on massive, fragile power grids.
And if we extrapolate even further into the future, the implications for off-world colonization are absolutely staggering. The extreme temperature swings and a brutal radiation on the surface of Mars or the Moon present the ultimate hostile environment. A traditional above-ground metallic habitat would require immense, dangerous amounts of nuclear energy just to heat and cool.
But a habitat built on the fundamental principles of the Walipini, buried deep beneath the lunar regolith for thermal mass and radiation shielding, utilizing advanced desiccant wheels and phase change evaporative cooling to regulate the internal atmosphere.
It completely changes the mathematics of survival. The technology we are currently refining to grow winter kale in Minnesota might literally serve as the exact thermodynamic blueprint we used to build the first sustainable human cities on Mars.
The ground beneath our feet is not just inert dirt. It is the ultimate untapped energy battery. We just have to be clever enough to plug into it.
Yeah.
So the next time you find yourself stepping out of a howling sub-zero blizzard, I want you to remember that heavy wooden door set into the snowy ground. The wave of heat, the lush green leaves, the absolute silence of a system working in perfect geometric harmony with the planet. It isn't science fiction. It's just physics. And it is waiting right below the surface. Thank you for joining us on this deep dive. Until next time, keep exploring.